Actually, I want to slideshow, set up slideshow. There we go. All right, we already did the T-ball kid. So let's look at a baseball player real quick. Oh. Man, now my computer's slowing down on me. Hold on a second. Don't need that. I lose electricity and everything goes crazy. There we go. Now my slide's not working. What the heck? All right, we're having some technical difficulties here. There we go. All right, we're back. We're back. All right, so checking this out. Now we're back. All right. So once again, I'm pretty sure I posted these slides on Google Classroom. If you want to follow along on the slides, you can do so. Might be helpful. All right. That's up to you guys. All right. So impulse, if we check this out, make that a little bit larger so we can read it. Impulse is the change in momentum. So if we check a problem like this, we look at a problem like this. A 0.144 kilogram baseball is moving toward home plate with a speed of 43 meters per second. When it was bunted, the bat exerts an average force of 6,500 newtons on a ball for 0.0013 seconds. All right, the pitcher throws the ball in the positive X direction. The force will act in the negative direction. Okay. What is the speed of the ball after the bunt? Okay. What is the speed of the ball after the bunt? So in this example, all right, well, we're always analyzing impulse. Okay. So impulse is equal to the change in momentum, change in P. Okay. Let's zoom in a little bit. Impulse is equal to change in momentum. All right. Where impulse can be force times time, that's what impulse is equal to the change in momentum is the mass times final velocity minus mass times initial velocity. Okay. So if we look at this, the force exerted on the bat is 6,500 times the time, which is 0.003, 0.0013, I mean, 13. Okay. The mass, okay? So I'm going to have minus. So the mass of the baseball is 0.144. And this is times the final velocity, which we don't know, and the initial velocity. Well, we know it's moving towards home plate at 43. Oh, can't see that. That's my bad. We know it's moving towards home plate at 43 meters per second. And that's how you would set that up. Okay, that's how you'd set that up. So you multiply these two numbers, you add that over and divide by that. So let's try to solve for velocity final. So all right, so let's see. What are you guys getting? Anybody want to share? Oh, I heard it. Oh, lost it. Oh, 102 meters per second. That is what I got as well. I got 102. All right. Where was I? There we are. All right. What is the change in momentum? All right. What is the change in momentum? Well, if we know our final velocity is 102, all of this is equal to our change in momentum, right? All of this is my change in momentum. So all you got to do for part B is answer that. All right. Part B, you're going to answer that. So put 144. All right, and I got about 8.266. Oh, it's adding, subtracting. So it's going to be, oh, this is a little tricky actually. So you got 0.144 times 102. Okay, so that's three digits after the decimal. 4 times 43. That's 3. So you're going to have, when you subtract them, you're going to have 3 digits past the decimal point. So I got an answer to be 8.496. Okay, and that's my momentum. Now, C says, what is the impulse? What is the impulse? Well, the impulse is over here. So whatever my momentum, change in momentum is, that's also my impulse. 8.496. Okay, so that's another impulse example. All right. So if we check this, I'll come back to this one. If we check out a concept question, one car crashes into a concrete barrier. Another car crashes into a highway barrier filled with water at the same speed. What is the difference between these two crashes? What is the difference between these two crashes? And you've probably seen these highway water barriers before. It's all applied physics right there. Well, if you think about this, if we think about this, all right, so my impulse is force times time is equal to my change in momentum, which is mass final velocity minus mass initial velocity. So if we think about this equation while trying to solve this, A, change in momentum. Well, the mass of the car will never change. Okay. My final velocity is going to be 0 either way, and my initial velocity going into it is the same. So my change in momentum is not an answer. I know it can't be A. B. Well, yeah, we'll go B. B, force times time. Well, if you think about it, the amount of time will increase because it's compressing. All right. So the amount of time is going to increase, which if this is constant, all of this is constant, my force is going to decrease. So what happens is my force and time are my answers. And then my momentum, once again, my momentum's constant. We're not really worried about that. So if we think about it, water barriers are put on the side of the road to decrease the force by increasing the time of a crash. Pretty fascinating stuff, right? All right, last example I'm going to go over today. Last example. Well, not that one. Here we are. Okay. All right, so that kind of looks a little familiar. A boy who is 2 meters tall shoots a 0.3 kilogram dart out of a blowgun horizontally. The dart lands 8.3 meters away. How fast did the dart leave the blowgun? What is the impulse? And C, if the dart took 0.0 seconds to exit the blowgun while being shot out, with what average force did the boy blow into the gun? All right, so this probably looks a little familiar, and this is my last slide for the day. So you guys will be able to work on your assignment. There we go. Let me get a new piece of paper. All right. So looking at this, a boy who is 2 meters tall. Okay. There we go. Okay. He has a blowgun. He's 2 meters. Okay. He blows the dart 8.3 meters. Just getting all of my information down. All right, he blows the dart 8.3 meters. Let's see. We know the mass of the dart. We know the mass of the dart is 0.3. Now, what we have to consider is when looking at projectiles, we have to look at things in the x direction. We have to look at things in the y direction. What all do we know? All right. Well, we know my acceleration in the x is 0, right? My acceleration when we're shooting horizontally, remember horizontally, acceleration in the x is 0, where acceleration in the y is gravity, negative 9.8. Okay. We know my x, delta x, displacement in the x direction is 8.3. My displacement in the y direction is negative 2. Okay. Let's see, what else do I know? What's my initial velocity in the y direction. If I'm shooting it horizontally, my initial velocity is 0. So knowing these three factors, we should be able to solve for time. Oh, that's a blast from the past. Okay, so what equation on your equation sheet do you think we're going to use to solve for time? All right. Hopefully, looking at these factors, you chose the delta x is equal to the initial velocity times time plus 1/2 the acceleration times squared. All right, so I'm going to plug these values in. So my delta x in the y direction is -2. My initial velocity is 0 times t. All right, plus 1/2 -9.8 times t squared. That should help me solve for time. Okay, so let's plug this in real quick. That's just 0. -2. I got my time to be, well, this isn't our final answer. About 0.64, 0.64. All right, that's my time. Now, remember, that is the only thing that is going to be constant on both sides, 0.64. So when we're trying to see how fast did the dart leave the blowgun, right? That's our question. Well, what you got to do is look at our x direction. Since we shot it horizontally, well, we know our distance, our displacement, and we know our time. So velocity is displacement over time, and we're looking at the x direction. All right, so how fast did it leave here? Well, delta x over time. All right, so my delta x was 8.3 over my time, which was 0.64. So 8.3 divided by 0.64. 2 sig figs, 13. My initial velocity is 13 meters per second. So in today's lab, or yesterday's lab, you're going to have to do that. All right, you're going to have to look at your factors you have in the y direction to solve for time using this equation. And from that, you're going to have time in the x direction, and you can calculate your velocity. Okay, so that's A. Let's look at B real quick. B says, what impulse did the dart experience from the person? All right, so what impulse? So B says, let me zoom in. B says, what impulse? So impulse is equal to the change in momentum. So we have final velocity minus initial velocity. All right, so my mass of the dart in this example is 0.3. Okay, let's see. Now my final velocity, I just calculated, was 13. What's the initial velocity of the dart? When the dart is right here, what's the initial velocity? Should be 0, right? should be 0. So to solve this, you're just doing 0.3 times 13. I got 3.9. 1 sig fig will be 4. So the impulse is equal to 4. Okay, so that's how you will calculate the impulse of your dart. Now, the last says, if the dart took 0.07 seconds to exit out of the blowgun while it was being shot out, with what force did the boy blow on the gun? All right, so this is a quick one. So impulse is equal to not only the change in momentum, but it's also equal to force times time. Okay, so we just solved impulse. Impulse is 4. It said, what is the force? I don't know. Times my time was 0.07. So all you got to do is divide that over. So 4 divided by 0.07. I got 1 sig fig will be 60. I got 60 Newton. And that's how you're going to solve a few of those examples from yesterday. Okay. Once again, you're going to be using, find your y values, use this equation to get your time, and that will give you your velocity. Impulse, just your change in momentum, and that's how you solve for force. Does that kind of make sense? He is very tall. Yeah, he is very tall. What, 6'7"? Around 6'7"? What that guy would be.
Why did you divide by 0.07 for the time?
Oh,
And C.
so let me show you real quick. If you can see, so I'm solving for force.
Yeah.
So force times 0.07 equals 4. So if you divide 0.07 over to this side, force will be by itself.
How did you get 0.07? Sorry.
That was in the problem. Let me go back to the problem.
I wrote it down.
Oh.
Okay, I see.
That was a good question. Any other questions? Okay, so the rest of the day, all right, you got another 15 or so minutes. The rest of the day, I want you guys to finish up that lab from yesterday. All right, if you are already done, the last 15 minutes of time class is yours. But hopefully that helps out. All right, helps out on solving the Nerf dart lab. Is there any questions? All right. Well, I am going to stay on the Google Meet. If you guys have any questions, you guys can always pop back in and ask. If not, I hope you have a fantastic weekend, and I'm super pumped to see you guys on Monday.
We'll see you, Mr. Bowers. Have a good day.
See ya.